Ooh, what's up, what's up, what's up, what's up? Welcome back. Today we're working on my image to ASCII neural network. So the idea is we have a picture on the left, we want to turn it into text on the right, right? If we look at this guy, he's made up of a bunch of different glyphs, and the idea is that hopefully we can recognize the image on the left with the fewest amount of glyphs possible, right? So you can imagine the most naive approach would be to just look at the brightness of the pixels, right? But this doesn't fit the form of something as well as if we do try to be a little more intelligent and fit the shape of the glyph to the thing underneath it. And so you might ask, why are we using a neural network? And the answer is here's an example of our sample. We have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 by 5 grid. We want to feed this into whatever process we're doing to figure out what we want to see in a glyph, and say that you have the number 1 in here. You want this to match approximately to the number 1, right? And so how do you do that? Well, what we're doing right now to generate our labels is we're kind of going through every single character, which there are 1,500 of them, and we're going through every single sample, which there are also a lot of. These samples are I don't know, there's I don't have a good feel, maybe 8,000 of them per image or something. And we're going pixel by pixel, and we're saying well, if we render the glyph of this guy, he's now in also a image, and we maybe blur him a little bit so that we can get some area of effect of the glyph, and then we compare him with this guy, and we do that for every single character, and we say which one had the lowest difference. And it turns out that the way we're doing right now is kind of expensive. It's maybe 2 seconds on the CPU for a 1080p image. And if we train a neural network that's really, really fucking stupid, but good enough, we get this approximately the same performance, maybe 90% as good in 0.01 seconds or 10 milliseconds, which is a 200 times speed up, right? So that's pretty fucking good, and we can optimize the neural network more. We haven't really looked into that at all. We might be able to optimize the labeling a little more, but we've put some effort into that already. We went from maybe 15 seconds down to 2, which is pretty good. Okay, so we've justified somewhat that neural network make thing go faster, almost good enough, but not quite as good, right? And so today's topic is we want to actually go the other way. We want to say that we have this character, and we might feed it some inputs and say, which one of these samples did this come from? And the reason for that is last stream we were doing some pre-processing of our images with the intent of making the output look more reasonable for our neural network, for our ASCII-fied images, right? So left is the input, and right is what we do to it before we feed it into our neural network. And the idea is that most characters are more dark than light, right? Assuming that you're doing white on black. So what actually ends up happening is there's only a very few amount of characters that are available in the upper half of the image, or the upper half of brightnesses, right? So we have these guys essentially, or kind of the ones that are over 50% brightness, and then all of these guys are the ones that we have to fit darker shapes. So if we want to have better fit of glyph shape to object, you kind of need to push the whole scene into the darker range, was kind of the thought. And so we were spending a lot of time tuning this last stream to kind of make it look like we keep our whites white and our darks dark, and we got something that we're pretty happy with, right? Here you can see we're blasting the contrast out of this image. But somebody in stream was saying hey, doesn't this feel really manual for an AI stream? And it's yeah, it does. And my initial thought was, well, we need some number, right? We need a number to say, how good is this? And we have to come up with that number. So right now we're kind of just pre-deciding for the network we think is good. But it'd be interesting to see if we could get a neural network to decide what the best transformation is for us, right? What's that saying? If you have a hammer, you like hitting stuff with hammers, right? Because so we have a tool that is neural network, and we want to use neural network to solve all of our problems. And so the thought is there are these things called GANs, GAN network. I can't remember what it stands for. Generative Adversarial Network. And these guys are kind of used to train a image generator right? So the idea is that like if you have they train something that says like I'm going to generate picture, make image, and then we're gonna take like a real picture, real picture, and we're gonna feed both of these guys into like this network that says like real or not, right? So he's going to say, like, this thing, do I think it's a real image or a not real image? And so the idea is, like, this guy learns to say whether or not things are real or not, and this guy is trying his hardest to trick this, right? So assuming that, like, the real or not real classifier can correctly predict which one's real and not real, the guy that is like generating images should eventually like trend towards something that looks more reasonable and realistic that would trick a human as well, theoretically, right? And so I think that we could apply a similar idea here. I think. Here's what I'm thinking. I'm thinking that we know that we want to pre-process our image in some way to make it look more reasonable after we do our like image to ASCII conversion, right? And so what if we created someone who says like, where did an image come from? Like which image produced ASCII? And we feed in our like ASCII image as well as like A and B, right? And my thought is we can apply some pre-processing step to like the input to this guy. So we can say we like feed A into the ASCII. We're gonna like inject some pre-processing step here and say, could you please learn the best pre-processing step that will make this output like most successful? And so I don't really know if that's reasonable, right? You could imagine that like if you gave this guy the ability to run like 2 or 3 convolutions and maybe like a couple linear things, you could maybe get something where maybe it would learn to like create like a sharpening mask or a blur or like a color change, right? Like who knows what it might decide to learn. But it would be interesting if it happened to learn something that correlates well with humans recognizing, right? Because like that's kind of like the end goal, right? We want a human to be able to look at a picture and say, that was the one, dude. That's exactly what I saw before it went in, and it looks like fucking close with when we turn into ASCII. So that's kind of my thought. I think hand wavy, probably this like which thing is ASCII is like pretty close to one of those like generic image classifiers. Right? So like we could maybe take like an image classifier who like we'll treat him as like a box of like a bunch of shit, and has like image classifier. And one of the like, you know, his outputs are going to be like cat and dog, right? And like airplane. And I kind of think we could just like lobotomize this guy, cut this stuff off, and take all of his like inner juicy, tasty parts of his brain and use them for what we want to do, which is this task here. And so we can maybe just like cut this stuff off and train something else, and we can like adjust his inputs so that instead of taking in 1 image, he takes like 2. And we can maybe start by trying to train someone who can determine, first of all, just if an image is ASCII or not, right? If we can't do that, then like this isn't going to work, because it has to be able to like use the features that it's using to classify cat, dog, airplane, dolphin, whatever. It needs to be able to use those to determine like interesting features about an ASCII image. So first we can try to say, well, find out if it's like ASCII or not. If that works, then we might be able to try to adjust it to say, well, now tell us which image this ASCII came from. Hand wavy. That's kind of where I wanted to go with this. See what happens. Yeah. So I think the first step is going to be to find some image classifier that we can just like plug in and just see where we go from there. Yeah. So let's get moving. So let's find a pre-trained model. So we can just like go Torch Vision, which is like the library that we're using that's like a PyTorch friend who has a bunch of like stuff in him, I guess, like hand wavy stuff. And we can look at torch vision image classifiers. And they have pre-trained weights, and so we can just kind of copy paste some code here, and let's start by just trying to see what like the existing behavior of this guy is, and see if we can run him at all, and see if we can get him to work with his like current state, right? So he's supposed to classify like maybe like cats and dogs and shit, and maybe we can just give it an image of a cat and see if it gets it. Hand wavy. Let's see. So you can say from torch vision models, import ResNet 50. They have a bunch of options here. I think I'm going to start with ResNet just because that's the one that it has in its tutorial. I'm sure that there are reasons why I might want to use like an image transformer or like one of like those other ones like DenseNet or FishNet or whatever. I'm not going to like think too hard about it. I'm going to assume that any classifier is going to be good enough for this task. That might not be true, and we can experiment with that later, but for now we'll just start with something. I know that there are also ones that are a little smaller, so I think that there's torch vision models. Is that actually, just scroll down here? They have ResNets that basically are like the same thing, but with more or less weights. What language is that? Is what? PyTorch? It's Python. Kind of, well, I mean, it depends on what you mean. Like, we are going to be writing in Python, connecting to a library written in C++ that then like runs like CUDA kernels on a GPU. So there's a little bit of like, it depends on what you're asking, I guess. Or if you're asking what is on the page, it's almost English. Almost, like RegNet Y32GF. Who knows? Okay. So let's just pull in one of these guys that seems like he's going to work like okay. So 75%, probably enough. 70%, maybe that's good enough, right? We can maybe sacrifice some accuracy for speed here. So let's start with the dumbest thing and work our way up from there, maybe. So we'll start with like ResNet 18, which is like the smallest one of the ResNet family, which is the one in the tutorial. So let's just do that. So we'll just start copy pasting and see where we get. So they say from torch vision models, import something. So we wanted to switch from the big one to the small one because we are weak little programmers over here with our weak GPUs. So ResNet 18 and ResNet 18 weights. And then they say that you can just instantiate it with the weights. So we can say model is equal to ResNet 18 with weights equal to ResNet 18 weights default. He says that that's not a known symbol. Did I spell this wrong? Where we see maybe ResNet 18 weights. So it does, it's capital N, of course. ResNet, not ResNet. Yo, what's up? I think, Nick, you might be the person who injected this idea into my head yesterday. Were you the one that was telling me that I shouldn't be manually tweaking my pre-processing steps yesterday? Yeah, okay, yeah. You nerd snipe me. We're gonna try. We're gonna try seeing if we can get the network to figure out something. Okay. So what am I doing? I am pulling in some weights, and then what else does this guy say we do? Once we have weights, presumably we can run this on something using the pre-trained model. Here we go. So they have transformations that you apply to an image before you run it. Okay. So we can say like model weights transformations. Weights transformations. ResNet 18 weights transforms. Transformations. Transforms. Who is apparently not callable. Can we like maybe just look at what this guy is? What is this guy? What is he? What is he? Property object. Sick. Love that. Can I like jump to definition? Oh, okay. I don't know why he thinks he's not callable. Object type of type property is not. Oh. What does he return? Self value transforms. I'm just gonna hit the. Even though it says that I'm not supposed to put brackets here, this says I am. So it does say it's not callable. Which is interesting. So is this just not? Am I just like not on the latest and greatest or something? Let's see. What does this guy return? He returns self-value transforms. What the fuck is self-value transforms? We can look at the weights here, and this guy is going to say that his transforms have some image classification, crop size, and image classification. Oh, I see. Here we go. This is really they do a resize, center crop, convert image, and normalize with mean of this, standard deviation of this. Okay, cool. Makes sense. Makes sense. Makes sense. I don't know why they're not letting me call it. Oh, because my weights are not. I see. I'm looking at the module, not this. I'm supposed to be looking at this guy here. Aha! This is what I'm looking for. Print this. What LSP are you using? I've yoinked Pyrite out of the Visual Studio. I think Visual Studio Code developed the Pyrite language server, and then I can use that from NeoVim, I think. I actually have to double check. I guess we can just say LSP info here, and it'll tell us. Yeah, Pyrite. Pyrite. How do I get out of this fucking window? There we go. Okay, so here we see, okay, yeah, we have a crop, resize, mean, standard deviation. Okay, sure, whatever. Looks like that's fine. Looks like it's fine. So then we apply this pre-processing step to an image. I guess, given that we see that, fuck. Where did it go? Where were we? We were here, here. So given that this image classification step does a resize and center crop, that kind of indicates to me that we can just feed it like fucking anything. And if we give it anything that is one of the classes that it should get, it'll like turn it into the correct inputs. All right, so we can just probably download a picture of whatever we're trying to classify. And then we should be able to, okay, so it's saying we set the model to eval mode. So we say model is this and model eval. We should be able to load any image and feed it in after we apply pre-processing steps. And then I guess we just need to find out what are like the outputs of this model. How do we find that? Get model weights. Get the weights enum class associated with each model. List modules, get model. Okay, so can I just say, no, that's not what we want. I want to know, like, what are the classes on this guy? Like, maybe ResNet will tell me. What is his output? So he comes from, what, he returns a ResNet, and the ResNet is a ResNet. How do I find out what his classes are? I just want, like, to know what types of images I should be feeding in. I guess it's ImageNet, so we can just look at ImageNet classes, and that will probably tell us. 1,000 class list. Ah, okay, here we go. So it's animals. We have, yeah, dog, fox, cats. Okay. Are one of these just like cat? All right, let's just, okay, we'll feed an image in of a cat, and we'll see what comes out, and then see if we can correlate that back with this later. So, cat. Cat. Here we go. We'll download this picture. Save image as, we'll go over to downloads, I guess. We'll just call it AVIF. I don't want to use an AVIF. That's a fancy format. Give me something simpler. JPEG. Here we go. Cat. And it should be, no, so we should be, say, weights is equal to this. Weights pre. I lost it already. Where did we get the transforms from? It was from the weights, right? Pre-process is weights transforms. Yep. Pre-process is equal to weights transforms. And then we just pre-process our image. So we say image is equal to image open home. Can I just does this let me use these guys? I don't know. We'll try it. Downloads cat.jpg. We import image. Sick. And then we should just be able to pre-process the image. Model input equal this, and then we should just be able to run the model. And then can we just ask like what the answer is? So we can say like print output. I don't really know what the output is. We'll see. Yo, what's up? It's going good. How are you? So we need to download some checkpoints. That's fine. No such file directory downloads cat. So I just do need to write home streamer. This. Run it again. Okay. So he doesn't like something here. Probably because I forgot to turn it into a tensor. So we can just say image open this guy, and then we convert him into like a torch tensor. And I think we might have to go through a numpy array first. I've been doing this. I don't know if it's like required, but I feel like I've needed it. I misspelled tensor. Okay, so let's try that. Okay, so that's doing something. Size of a tensor must be of a tensor A 175 must match the size of tensor B 3 at non-singleton dimension 0. Okay, so clearly we can't just put in anything. What is this? What is this? What is it? We have a uint8 thing. Looks like 2 dimensions. Let's just double check this. Okay, we'll do this at the top before we do anything else. We'll just return or exit, so that we don't have to run all the other shit that we don't care about. Import sys. And just run it. Oops, and then we want to print its shape and its dtype. What am I looking at? So it's 175 by 287 by 3, which is height by width by number of colors, which makes sense. And I think that maybe Torch Vision expects these guys to be in like batches. So I might have to say unsqueeze to add one dimension at the very bottom, I think. Oops, I should actually not do this exit, and we will maybe not do this part for now, and sys.exit 0 here, and let's see if that gives us something that doesn't crash. Still no. Size of tensor A must match the size of tensor B at non-singleton dimension 1. All right, let's get a little look a little closer. Let's look a little closer. Should it be model input? Yep, it should. You're right. But we're not even there yet. So okay, so we have an image. And we're running these pre-processing steps. The transforms are. We saw they were this guy. So let's look a little closer at him again. So he is a transform that is image classification. And what does he expect for his input? He's norm, and where are we crashing? We're crashing on normalize. So it's here. So what does this guy expect? He expects channel by height by width, not width by height by channel. Okay, fine. Okay, so here we just need to somewhere swizzle some dimensions around. So here we go image, transpose, I think. transpose torch, which I think just says, like, if we have height by width by channel, can we turn that into channel by height by width? Returns the tensor that is transposed given the dimensions dim0 and 1 was swapped. Yeah. But we actually don't want, like, a full swap. We want, like, we'd have to swap twice to get what we want, which is maybe fine. Yeah, sure. So we can swap dimensions 0 and 1. Sorry, 0 and 2. So this will go from height, width, channel to channel, width, height. And then we need to swap dimensions 1 and 2 to go from channel, width, height to channel, height, width. Yeah, that seems reasonable. I don't know if there's like a more direct way to do this, but that's fine. And so now we should see, when we run this, we should see a shape that is 3, 175, 287. Perfect. And now we can pre-process. We can say print, pre-process. Oh, not, we want to print model input. Did we get something reasonable? I wonder what a type system would look like that takes matrix dimensions into account. Yeah, I wonder if you can, like, balance the flexibility of being able to, like switch them around like this without it being too cumbersome. Because it would be nice. I would love to have a compiler tell me that I fucked up. But I just don't know how, like, I don't know if you lose too much flexibility by doing that. Okay, so I guess now we can print the model output. It would be a different type after the switch. Yeah, I can see that. I just wonder... I wonder if it would be too limiting. But maybe not. I guess, I can't imagine why it'd be that much a problem. Okay. What do we see here? So we have a lot of outputs. This is probably, like, however many classes there are. Is probably the scores here. Yeah, so we have... For our one image, we have 1,000 outputs, and those 1,000 outputs are probably the ImageNet classification, so we could probably just say output.max. And we want the index, so we say dim equals 1. And this, then we say value index is equal to this. And then we print index. If I remember correctly, which I might not. So he's saying this is class 281, and so we have the class list here. Tabbycat, which I believe is what we gave it. I think that's the image we downloaded. We downloaded this guy. Is this a Tabbycat? I don't know. Tabbycat. Yeah, that's what we gave it. Sure, and like just for good measure, let's like look up like dog, and say this is dog.jpg, and let's just double check that we do in fact get what we expect. So we just run the script again. We get 207. 207 is golden retriever, which I think that is. I don't. Most adorable dogs and puppies. I'm pretty sure that's a golden retriever. Pretty sure. Are any of these... it doesn't say what that one was. Okay, whatever. I'm pretty sure. Pretty sure. We can look up golden retriever puppy just to double check that that's... Yeah, pretty sure that's the fucking same thing. Okay, so we can, in fact, run our network that we downloaded from the internet, saying ours is a stretch here. That we now understand its inputs. And now, let's lobotomize them. Yeah. So the next thing that I wanted to do was I wanted to give it 2 pictures. One, which is just like our normal input, and another that is our ASCIified version of the picture. And just see, can you classify which one is which if we do something that I think it's called transfer learning? I think. Using transfer learning, which I'm pretty sure is just like you cut off the head and you replace the outputs with your own, right? Like right now they have like 1,000 outputs and we just want 2. So what do? They have their data transforms, whatever. I don't really care about that. Loading data, don't care about that. I want to know, like, when you load the model, what do you do? So they have their model, blah, blah, blah. Model's an input here. So I don't really care about that either. I want to know, like, how do you, like, make the model? Here we go. So they have this model that is a ResNet 18. They say number of features something. They take the number of features and they output 2. So 2 is probably their, like, output classification in this case. And they're, like, replacing it, I guess, with their new thing. Yeah, okay, that makes sense. So probably if we, like, looked at the inner workings of this guy, we went to our little ResNet here. When they run their forward pass, they do, you know, a bunch of shit, a bunch of other shit, a bunch of other shit. And at the end, the last thing they do is this thing called, like, FC, which I assume stands for final connections? Maybe? Who knows? And that's, like, their input is, like, whatever the output of the stuff before him was, and their output is just the number of classes. And so we're just going to be replacing that with 2, and we're going to train only that part. Cool. Fully connected? Maybe. That seems reasonable. Is linear and fully connected sound like interchangeable? I'm pretty sure that's what it is. Yeah, that sounds right. Yeah. Good call, good call, good call. Okay, so then I think that if I remember correctly, you need a way to, like, freeze all of the other layers. You don't care about the rest of it. So, or you don't want it to, like, change the rest of the network. You only want it to change the last piece. So somewhere in here, they must freeze all of the other weights, probably before training. So here, I could have sworn I've seen this somewhere. Train and evaluate. Yeah, okay, here. So here, they iterate all parameters, and they say, don't fucking track gradients for any of this. I only care about the end piece, and that's what I want, because the end result of this, 1, I want it to go fast, zoom, but 2, I want to make sure that the, like, how do I say this? We could maybe hope that the existing neural network here has learned to extract information about images in a way that, like, is, like, relevant to humans, right? If it's looking at, like, cats versus dogs in, like, a normal picture, hopefully the things that it's looking at are, like, things that we would think about when we look at, like, a cat versus a dog. And so if we then, like, say, okay, now here's a bunch of ASCII images, I'd worry that we're straying too far from, like, the general human understanding of what things look like and moving it towards, like, a very specific understanding of what ASCII images look like. So I want to, like, by freezing all of this stuff inside, we're kind of saying, like, keep whatever you've learned about the world that's, like, more general, and then only specialize this, like, one final piece. That's kind of what I'm hoping will happen, but who fucking knows? I don't know. we have to try it. Okay, so let's do this thing. So we look at his model. We look at the model, and we say for param in model, turn off gradients. Then we replace the last piece of the model with our thing. So here we have 2 is correct for us as well, because we're just trying to classify ASCII or not ASCII. This is model. We're not going to go into eval mode, and we're going to import torch.nnsnn so that this works. Cool. So we put in a little linear layer, bing, bang, boom. Then we're going to have to, like, train this in some way. So what's our training process going to look like? It's probably going to look very similar to our existing training process. We're going to load an image, run it through our network, generate the ASCII representation of it, then feed it in. Okay. So before we do any of this, let's actually formalize this a little bit. So we're going to write this as a train ASCII classifier. And let's open that guy instead. Train ASCII classifier. And I guess he's going to be doing something that looks pretty similar to what we're doing in our visualization script or our benchmark script, where we... nope, not this one. Visualization script. It must be closer to this. So when we try to get our image output, we load an image here. So let's actually start making functions here. So we'll call this def test model, which just does this, fuck this. And let's start looking at something more related to what we're looking at right now, which is how do we generate our ASCII image? Perfect. So we'll call this gen ASCII image. And it's going to look something like this. So we can kind of use this as a starting point. Paste, here we go. And so here he's got an image sampler, okay. And that's where we get the image from. We have an ID, which is like which image we want to look at. We get the image, we open him, convert him into black and white, which I guess we still want to do here, okay. And we put him on some device. Sure. And this comes from the glyph cache, actually. So we have a glyph cache, which is like all of the characters that we could render. This is where they come from. Okay, and we're just matching up the devices because everything, we need them to line up. We extract samples from the image, which makes sense. So we'll just do that, okay? That should all work. We get labels for samples. So in our case, we are going to be running them. I guess we'll run them through our neural network because that's the fastest. So we can just kind of yoink this guy. So we'll copy paste these for now and we'll figure it out later if they should be split up. Which means that back here, we can just say get labels from network. Cool. So we will label them like this, and we need to pass in the network here. So here we just need to take in our neural network. And then we create a renderer which renders the image. Okay, cool. So text render that comes from the glyph cache renders the image as text. And then I guess at the end of this, just for testing, we will save that somewhere. Just to make sure that all of this is doing what we expect. We need to copy paste some imports. So I guess the lazy version of me will copy paste this and then just delete anything that it says we don't use. There we go. There we go. This is imported twice. Not used, not used, not used, not used, not used. Cool. Yeah. Okay. So we should be able to say, oh, we missed a couple. Self, server's not defined. Here we go. And now we can say gen ASCII image. And we'll just pass in some specific picture just to get things working. So we'll just pass in this guy and just see what comes out. Oh, and he's got a lot of arguments. So here we'll say the image path is actually what we want to pass in. Oh, no, we're using the image sampler. I see. Image sampler with ID. So we can load an image sampler, which here we were using nested dir image loaders. Seems reasonable. So image sampler is equal to nested dir image loader, which will just load images from some directory. So we know that we have like a validation data set here for our neural network already. He needs some other stuff. So he has sample width, sample height, glyph cache. So, which means that we need to generate our glyph cache, which we've done before. Device is equal to CUDA for now, because we want to run stuff on the GPU. And here we generate our glyph cache, which is this guy, our nested dir image loader. We can probably just copy paste some of this stuff here. Copy paste, and later refactor. Okay, so we have sample width, sample height. We create our image loader from the glyph cache, and we just need the data path. So data path is equal to val. Cool. And so then we should be able to generate an image from our sampler with image 0, with our glyph cache, and our network, which we haven't loaded yet. So we're going to copy paste the code that loads the network from here. Boom. Boom, boom, boom. And we just need to copy some imports as well. Coding by copy pasting, the best way. Best way. All right. And here, I guess we can maybe hard code these parameter paths for now and factor them out into script inputs later. So when we run visualize, we actually have these guys right here. We can just copy paste them. So we have what we've decided are good params. So network params path is this guy. Like this. And the weights are this guy. All right, we should be chilling. But the weights need to be... Okay, what is it like? Load model params takes path like. So, what's the problem? Argument of type literal cannot be assigned. That's fine. That'll probably just work. And the network weights, do we need to like load them? No, I don't know why he doesn't like those. Strings are path likes, but I guess we'll just run it and see. Okay, so this should have, after all of that, written out an ASCII image to test.png, I think. So we should see here. Test.png modified at 1348 on January 4th. That doesn't sound right. We wanted January 6th. Did we not write it out? We did. Print hello. Let's just make sure that we actually got to where I think we're getting to. Did we type all the code correctly? No. Okay, so what the fuck is going on? What the fuck is going on? What is happening? Am I high? Oh, I'm running the wrong script. That would do it. Train ASCII classifier. There we go. Hello, hello, hello. Okay. Everything ran, and ls-l, we should see test.png updated on January 6th, just now. Perfect. And let's take a look at that guy. Just to make sure that he is something that resembles something. Okay, cool. So that's an ASCII image. Perfect. Perfect, perfect, perfect. Okay. So now what? We want to create a training loop for this neural network that will classify whether or not we generated this image or not. So let's make this function load model, or we'll make a new one, I guess, load model. And he will do this stuff here. I guess we'll make get model weights one function, and he will just say this guy, return this, and we'll say load model with some weights, and that's just gonna do this stuff. Boom. So here we return the model. Okay. Cool, cool, cool. Gotta head out. See you later. Okay, catch you later. So this guy we can replace with get model weights, and this guy we can replace with load model. Cool. Preprocess is still weights with transforms. And then we can say, take all of this stuff and say, move it into a function called like def load image for model. And that's this guy. He loads the image, does the transposes and stuff, pre-processes it. And we'll take in the path here. feed this and this. And then we return the preprocessed thing. And we might also want to say, here, he takes in the preprocess. And I think we're kind of chilling now. Kind of chilling. So test model now will feed in preprocess to what? Model input is equal to load image for model from some path val, or what we were looking at before. We were looking at home streamer downloads dog. We were looking at that dog image, and we've passed in preprocess. And I think all of this should still work. So let's just double check that. So we'll comment this out. Or I guess we'll call this def test gen ascii, like this. And then just at the bottom here, we can call test model again, just to make sure that like all of those changes resulted in still seeing the doggy. Tensor 0. So looks like maybe not. The index was not supposed to be 0 here. It was supposed to be a dog. So what changed? Get model weights. Load model with the weights. Oh, because we lobotomized him. Okay, 463, which was the golden retriever. I think. 463, 463. Bucket. Fuck. That's not right at all. That's not right at all. What did we fuck something up? So we reload the model with the weights. We apply those weights to this thing. Why is this different now? Print output. It was working so well. Or maybe we didn't do model eval like we did before. 207. That was what we saw before. 207. Golden retriever. Okay, we're back. We're back, baby. It's weird that that model eval is having such a large effect. That's interesting to me. Right? Like all of a sudden it thinks if it's not in eval mode that the dog is a bucket, which does not line up. But maybe the output is different in that case. Here the output was... No, that was still right. All right, there's something weird going on there. But maybe we ignore that problem and move on with our lives. I guess we should understand it. We should try to understand it. So, model eval changes output. What does that mean? Fixes some of the model's parameters, e.g. for batch norms, collected statistics instead of actual batch statistics. I see. Oh, instead of actual... I see. Sure. Sure. Okay, I mean, that seems reasonable. Okay. Okay, so now what do we want to do next? We want to lobotomize the model, prepare him for our ASCII or not ASCII, and we need to like make some training loop. So let's see. What are we going to do? We're going to take in some arguments, which we are going to maybe steal from our other training script. It's probably going to look pretty similar. Right, so we're going to have some training data that we're going to work with. That's still true. We have an output that we're going to work with. Where are we going to write the outputs of this network? For now, we won't do that. And which device do we want to train on? That seems reasonable. Seems reasonable. So we call main with these arguments, and the arguments are going to be training, data, path, and device. Okay, and if name is equal to main, we call main with this weird bullshit that I do on every script, which basically says run the argument parser, turn it into a dictionary, and pass in the names of the variables as arguments to main. Okay. So we are going to do all the stuff that we did at the beginning here. Device is now passing as a parameter. Don't have to worry about that. Data path also passing as a parameter. Don't have to worry about that. Network weights, I guess we can maybe pass those in as parameters as well. So we can say here, network weights comes into network weights. And the network params comes in as network params path. So this is the network that we're running to generate our ASCII representation. Cool. I actually think we actually have to be a little careful here. We have to generate our glyph cache with the character codes matching what our network expects. So it's network params car codes, I think, is the input here. I think. We'll see. We will see. And then everything else in here seems reasonable. Boom. All this goes into main. And here we take in network weights and network params path. Okay. Starting to come together. This data comes from training data path now. And otherwise, we're looking good. Looking good. Okay, so what's our training loop look like? He's going to do something. Who knows? So first, I guess we need to look at the model we're actually training from. So we're going to call this, instead of network, we're going to call this image to ASCII network so that we can distinguish. This guy is going to be actually fixed. So we can maybe do the same thing here where we look at his parameters and say parameter requires grad equals false so that no gradients are put on this guy. And then we probably also want to put him into eval mode. Okay. Cool. Then after we do that, let's just make sure that if we generate an ASCII image here, after making those changes, everything still works as we expect. Let's just make sure. Okay, so let's run the script again. Python 3, train image ASCII classifier. It's going to start saying you need to pass some arguments. And so let's start doing that. Training data is equal to val for now. Network weights is equal to this guy. Network params are equal to this guy, and device is Huda for now. It's not car codes, it's probably maybe car map. We could also maybe look at it, but you know, sometimes we're a little lazy. Okay, there we go. So that's working, and let's just double check the output of this guy is still sane, which he is. Great. Now. What do we want to do here? We want to train. So we need our model to train. So we'll say classifier model is equal to load model. Yes. Classifier weights is equal to what do we call it? Get model weights. Let me feed this in here. Okay. And our training loop is going to look similar to this training loop, but it's going to be not quite the same. So let's start with copying and then delete a bunch of stuff that we don't care about. So we need an optimizer. Makes sense. So we'll just copy paste the same one. Maybe we'll find out that this is not reasonable, but for now we just want to start with something, and we can iterate. We need an optimizer. We're gonna get some data, which we're gonna have to figure out later. So to do get data. For now, we'll say data equals none so that something is there. We're going to zero out the optimizer. So all gradients go to 0. Sure, makes sense. And then we're gonna run our classifier model. Okay. Makes sense. Makes sense. Then we're going to have some sort of criteria of success, which makes sense as well. And And then we're going to have to generate the labels. So labels is equal to none. And the label will just probably be which one is correct. Okay, we'll figure this out later. Run the backwards pass, run the step. We have an external counter in this version, which makes sense. So we say we print out our step and our loss, just to make sure that we see it going down. And then we also were saving checkpoints, but we don't have to worry about that right now. Okay. So hopefully what we see here is when we feed in data and labels, loss number go down. That's kind of the only thing to do now. And so now what we want to say is, where is the data coming from? So I guess we're going to get some data, just pull out an image from our image sampler. The image sampler right now is kind of tuned for our other training process, so we're just going to pull out some images manually. So what can we do here? We can say that the max images, or num images, is equal to this. These are all the options that we have, all the images available to us. And we can just set a batch size, probably. And then for each batch, we're going to say what? Take some random numbers in the range of 0 to num images. And we want batch size of them. 5 images. 5 indexes. Okay. We're going to say that the paths are the sampler images I. Yeah. Not I. Well, okay, let's make a new function so that we don't have to worry about, like, fucking up global state. We can say get images. Yeah. And we will ask for some number of images. And we're going to take in the sampler as well. So we're going to do the same thing where we and the batch size. Okay. So for I in range this, we are going to load the image, I guess. Load image for model. But we might want to convert him into ASCII. So maybe we do this. We load the image from the sampler images I. No. Yes. Image ID like this. So we get the image ID, we pull out the path for that image, we open him, convert him into a tensor, and then we say if we want to convert him into ASCII, we run our network on him, which means that we have to do this stuff. Okay, that makes sense. So we'll say def image to ASCII, and this is going to take in, or maybe we'll just say load ASCII image. Gen ASCII image. That's already the right. So here we can say if this is ASCII, so we'll just say rand is greater than 0.5, 50% of the time. Really? No rand? Random.random maybe? Okay, so if 50% of the time, we want to turn this into ASCII. So we'll just say gen ASCII image from the sampler and the image ID. We also need the glyph cache and the network. So we'll just take all those guys in. Glyph, cache, and network. Okay. Yep, that's it. And otherwise we just load the image. Yeah. Sure. And then what? Print image.shape. So let's just make sure that the outputs of these guys are the same. So we're going to say for the ASCII version, we have this shape, and non-ASCII, we have this shape. And let's just, instead of doing anything reasonable in main, just after we load up all our shit, instead of training, we'll just say get, actually we can just call get images in our loop and we'll see what happens. So we'll say get images. And what are like multitude of inputs here? We just can copy paste them and fill in which ones don't work. Num images, 5. No. We don't pass in num images. This can come from the sampler. Batch size, 5. Glyph cache. Net is image to ASCII net. This guy. Fuck you. Num images is sampler. Num images. This. Boom. Sampler, glyph cache, image ASCII net. Should work. Should work. Obviously doesn't, right? Because why would it? What is this saying? Received an invalid combination of arguments. Got inted, expected one of int tuple vince. Okay. All right. So here we just go boom, boom, boom. Make them a tuple of 1. Okay. So here we got ASCII has torch size of 2016 by 2086. Non-ASCII has something by 3. So this is a monochrome image with height 2016, width 2816. Non-ASCII is this. Okay, so we just have to make sure that we put them both to monochrome, I guess. Except do the inputs to... Yeah, the pre-processing step of the network, like the classifier, will probably fix it if it's not monochrome. But we should make them both monochrome just for like consistency. So here we're gonna say, we're gonna convert this guy to mode equals L, and then they should have the same shape. Yeah, they're both height by width. One of them's bigger, but that's fine. When they're ASCII, they're massive, but because our like glyphs are so fucking big, but that's okay. And then here we can just now, what architecture are you using? Those sizes seem really big. Well, they're really big because when we generate our images, each image is like 36 pixels wide or something, and they came from things that are like 6 pixels wide. So we'll just allow, like, we'll load the image, and then before we run ResNet, it's going to run that like pre-processing step, which basically converts it into like a 224 by 224 image for us. Basically, I'm just like not going to worry about it. Okay, so we need to do those transformations that turn it into channel by width by height instead of width by height by or height by channel. So wherever we did this stuff. Yeah. Okay, boom. And we should probably take this comment here. Boom, boom, boom. Except in our case, channels is always going to be 1. So we actually don't have to do the same thing. We can just do image unsqueeze on dimension 0, which goes from height by width to channel by height by width. Where C is channel. We'll just make that explicit. Okay. Seems reasonable. And then we pre-process. And we can maybe pre-process them all at once. Pre-process it now. Sure, we pre-process it now. So image is equal to this. And the label is if we were ASCII or not. So is ASCII is going to be this random thing. Yeah. We say if is ASCII. And the label is ASCII. So now we can just say we have data is equal to this, labels is equal to this. Data appends the preprocessed thing, and the label append. I guess they want this as an index, but that's fine. We'll just append is ASCII for now. And then probably the output we want it to be in like torch tensors. So data is equal to torch tensor data. I think that that'll just work. Labels is equal to torch tensor labels. And then we might need to convert these into indexes. So we'll just say to torch int 64. Okay, yeah, I think this is all coming together. Print data, we just return data labels. Okay, which means that now in our training loop, we can say data labels equal this. Yes, 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 yes. And then I think this might just work. Cross entropy loss is still reasonable. We have two outputs. Let's just print data.shape and labels.shape to make sure that everything like lines up. Labels. All right. And here we're missing some input, so pre-process here, which is going to come from classifier weights.transforms. Yes, yes, yes. I think we're there. So like, this might just run. No, it never works. Never works the first time. We should never expect it to work the first time. I see. So the input to pre-processing is expecting a RGB image, which sucks. Does suck, but we can fix that. We can fix it. So here, I guess we just need to repeat 3 times. And that should just say that the RGB values will all be the same, and that's okay. Which should give us something of 3 height width. 3 for how many colors there are. So let's see. Number of repeat dims cannot be small. Fuck off. Okay. Image or tensor repeat. We'll look up the fucking docs. The ResNet wants RGB. Theoretically, yeah, apparently. So we repeat sizes. I see. So we have. Do we just need to do like 3, 1, 1 or something? There we go. Okay. So that's working reasonably. Only 1 element tensors can be converted to Python scalars. Okay. So what do we have before this? Oh, it's datas. Data? No. Yeah, that should be fine. What's data here? Print data. It should be a list of tensors, which I thought auto-converts. Data has tensor, then tensor, then tensor. So what's the fucking problem? What's the fucking problem? Oh, is it torch stack, actually? Like this? It was like this, maybe? To convert a list of things into, like, a bunch of them. Yeah, oh, no, almost. Expected all tensors to be on the same device, but they're not. Okay, so we're close here. Now we just have to, make sure... Why are they not all on the same device? That's weird. That's weird. I guess we need gen ASCII image. Oh, because here, these ones are correctly getting put onto the CUDA device, and this one's not, probably. So here we just have to say device is equal to glyph cache dot device. Propagate that on, baby. Expected tensor as element 0 and argument 0, but got bool. Oh, because these guys, the labels, I'm pushing bools, but here I need to turn these into torch tensor. Bool. Yeah. We're close. We're so close. Yeah, okay, sick. So we got out 5 samples. We have a bit of a mistake here where we had an extra dimension on something, but let's just see. So we have 5 images that are 3-channel 224 by 224, as well as 5 labels. So 5 datas, 5 labels. Sick. And now we've just fucked up that the images want to be float tensors. So probably somewhere. Let's see. Let's see. What's this guy doing? Okay. Probably we just want to say, wait, why are they, should they not already be float tensors? Everything should already be floats. But maybe it's not. Print data dtype. Let's see it. Let's see it. Float 32, yeah. So it's already input type float to torch CUDA float tensor and weight type torch float tensor. Ah, good eye. So it's that we have to put the something. The classifier model has to go to device. Probably. We have to say, please run me on the GPU. Yeah. Okay, we're close. We're close. Another one also has to be on GPU. So let's go back to our other training script and look at what are we looking for? Device. So we have the glyph cache on the device, the network on the device. Who is not on there? So it's the cross entropy loss. Expected all tensors to be on the same device. Oh, the labels maybe are also need to be. Yeah, our labels need to be to glyph cache device as well. Hopefully that's the last one. Okay. Okay, so now let's get rid of some of these like prints that are spamming us. And hopefully we see iterations happening and loss number go down maybe. Okay. So number not necessarily going that down. Oh, okay. There we go. It's kind of, it's trending downwards. It maybe. Let's give it a sec. Oh, what the fuck was that? Kind of boosted up there. We might have to like lower the learning rate here. Okay. The number is going down. Pretty like reliably down. Which is good for us. Maybe what we should do is at some point try feeding it. We need to feed it some inputs and see if it gets them right. So let's do that. So we'll say every 10 iterations, if I% 10 is equal to 1, we say equal to 1 so that the first iteration also does this. Throw a print in here because this guy is overwriting himself, so we need to put a new line in here so that we don't lose him. And let's just say what? We say classifier model eval. I'm put it back to train later. We say with torch no grad. We probably are missing some of these in a couple other areas actually, but whatever. We load some images. We'll just load some more. Fuck it. I don't really care. And we will then run the model on the data. We'll just run it on 4. I guess that's fine. And we'll say that the output is this. And we'll just print out the labels is equal to, I guess we need to get the maximum. We see which one is the highest value here. So we say label or output.max dim equals 1. And then we get the indexes, not the values. So output labels is equal to this. And then we can just say print labels equal output labels. There's only like a few, so we can probably just look with our eyeballs in that case. Okay, so initially he got just by chance on like off rip, he got most right. I guess we should probably try to do more samples here just to gain like some sort of like statistical significance, right? Maybe 5 isn't really a good answer here. Okay, here we're seeing that it got a bunch wrong. Learning rate feels too high. I'm just gonna drop this a little bit. By a couple orders of magnitude. Okay. Maybe we just have to give it a second. It does feel still too high. It's still like jumping around. But maybe that's fair. Maybe it's got to take some time to figure out what's reasonable, what's not. There's a lot of stuff in the network. We did actually, you know, I'm gonna go back because we did actually see before that it did look like the number eventually did start to go down. And so maybe let's do this. Maybe we'll allow for more iterations. Maybe even like 50. Yeah, 50 seems fine. And let's try to run this on more images. I don't know if we're gonna like run out. Like if I say like 50 here, is that just gonna like fuck my GPU? Who knows? Let's find out. And let's say sum over 50. And let's just kind of we'll start there. We'll start there, and that'll tell us like how many got right of how many could have got right. That does seem like it's super slow. Holy fuck. But that's okay. Okay, so we got just over half of them right at step 1, and let's just give it a bit of time, you know? Let's let it see. Let's see if it does something. All right. Okay, so number I do think maybe trends out. It's so hard to see without like any graphs. Eventually, I will have to like make some visualizations for this shit because it's like staring at the number is like 1, not very good for stream. 2, not very good for my brain and my mental state. Okay. But we did see after 50 iterations, the number that it got right did go up, which is good. So we are training something that can classify between ASCII or not ASCII, which is like obviously like a really easy task, right? It's like, is this like black and white and like just like two-tone and color, like whatever? Like the ASCII images are like very easily identifiable. So I'd be like really disappointed if we didn't get this right, but that is a good sign. Yeah, okay, so after 100 iterations, it's getting it perfect. Now, obviously, again, we're not using like training and validation sets, so it could be like memorizing shit, but that's like a good indication that we've learned something, right? Which is good. We like the network has the ability to distinguish these things, which means that hopefully it will also be able to distinguish which image. Yeah, we'll see. How many parameters in the model? Like a fuck ton. This is like way overcomplicated for what we're doing. We're using ResNet 18. So what is that? ResNet 18. Where does it say? I can sort it alphabetically, so I should be able to fucking figure this out. 11 million parameters, so like a lot. But this is just like the first test task. So the next thing to do is to try to adapt this to now, instead of trying to say, am I ASCII or not, we want to feed it 2 images and say, which one did you come from? Yeah, so hopefully that will work. Let's see. How can we like formulate this problem? So what is going on in this ResNet model under the hood? What is he doing? Excuse me, I don't want to delete code here. I want to jump to definition. There we go. Okay. So forward impl. He does some convolutions. I assume that BN stands for batch norm. I assume that ReLU stands for ReLU. Some pooling, runs some layers, does some averaging. And so then he uses all of these features at the end to do his classification. So what is like the input of my fully connected layer here? 512 times block expansion. So there's like a lot of features coming in here to each of the classes. And so I would think here, where was I? Sorry, I got lost. So I would think that like basically if here we said like store output of X for image 1, store output of X for image 2, and store output of X for ASCII, then we did some sort of like, so we'll call this as A, we'll call this B, and we'll call this X. Sure. So then we could maybe do like a connection of, we could feed in B and X together. And that will either give me 1 for this is me, or 0 for it's not me. But that's not really what we want, because like you could imagine if you have a pretty good match and an even better match, you don't want the answer to be like yes or no. You want it to be like, which one am I? So I guess instead we feed in all 3 together. And if it's A, it will be 0, and if it's B, it'll be 1. Yeah. That seems reasonable to me. So we can feed it. We can try to say this will give me something in the range of 0 to 1, or like negative infinity to infinity, right? Like negative infinity, whatever. Something that we can bisect to say whether or not X came from A or B. That seems reasonable. That seems reasonable. I'm gonna go to the washroom and think about this for a second, but I'll be back in like 1.5 minutes. Yo. Okay. Yeah, I think that's reasonable. I think it's reasonable. So, I guess. We need to. We need to like maybe deconstruct this guy a little bit. So, here, when we load the model, we might, does it make sense to like split this guy into 2 components? So here we have the parameters with no gradients. We will kind of want to like skip this step. So I wonder if it makes sense to like subclass this guy and kind of figure it out from there. Yeah, let's try that. So forward goes through forward impl, and we kind of want to just like inject a new function on him. So I guess we can say class what? ResNet classifier. This is kind of tricky because this guy creates this guy with a bunch of like inputs here that I don't really want to copy paste. Can you just like add a function, something after? That's silly. Here's what we'll do. We'll make a function that's like def featureize, I guess. And we'll pass in the model as well as the input. And we'll just copy paste this for now. Which is bullshit, but it is what it is. So we'll just kind of like whomp, model all these guys. And then we return X at the end. Okay. Yeah, reasonable to me. Then we have to adjust our input here, and our data is no longer going to be he's no longer going to be one guy. Let's see. So what's he going to do? He's going to load 2 images unconditionally. And then he's going to turn one of them into an ASCII image. Okay. So can we batch size? Each batch is going to have 2 images, 2 image IDs. And we'll call this for image A and image B. Yes. That's coming together. We'll use the term ID here so that we can distinguish from the loaded image. Yes. Okay. So then we load both images with this code. I guess we'll say path A is image A ID here. Path B. I guess we don't need them both. We only need it because this guy handles the image loading for us. So we only need the path in this case. So we'll say which image is going to be random 0.5. So we'll just say which image is this. Then, if which image is true, what are we going to do? What are we going to do? Thinking. So I guess we're going to load both of these. So we're going to load from path A, path B, and then we're going to say ASCII path or image ID is going to be is there like a ternary statement in Python? No, right? We just have to do path A and then or image ID A. And if which image is true, this is now ID B. And then here we say A if B else C. Oh, I like that better. Okay, so ASCII image ID is equal to... What a weird way to write that. Image ID A if which image else image ID B. And I guess now we should call, this shouldn't be which image. It should be called is image A. Yeah. Okay. Then we load from the ASCII image ID. And pre-process all of these guys. And we can I think that we can set this up as like our data is going to be A, B, ASCII, A, B, ASCII, A, B, ASCII, right? And then we can reshape them after. So we'll just append preprocess image A, preprocess image B, preprocess image ASCII. And we actually have to do this like height width shit for all of them. So we should actually just make a function quickly. We'll inline it for now. Later we'll figure it out. That is what like load image to tensor takes in a, or we'll just call it PIL to tensor. Yeah. Which is a lambda that takes in a PIL image and just runs this shit, except it's 2 operations, so we can't make it in a lambda, so we'll just say def PIL to tensor like this. Image, and it's just this. And I guess it's also, this isn't PIL, this is to width height to C, fuck, HW image to CHW image. There we go. Sure. Image equals image on squeeze 0, image equals image RP. Yeah, like that. Sure, return image. Sure. And so then we can just, for all of these guys, say HW image to CHW image. All right. Oh, god damn it. HW image to CHW image, this. And then we drop one of those. Okay, and then labels append is image A. Okay, so then our data is we stack all these guys together and then we reshape it to be of shape. We have 3 images per batch. We have batch size, number of batches. Each of them is going to have 3 images, 3 channels, 224, 224. And I don't actually know that those numbers are right, so we're going to say batch size, we'll call it n. Number of channels, height, width is equal to data.shape. And now we're going to reshape this to batch size 3c height width. Yeah. And n is not access because we don't actually care about that because we should assume that it should be 3 times the batch size. And it's actually like this. Data 0 shape. Right. So each of these is one image. Data 0 shape. It's the first element in here. It has CHW. We go back here. Boom. Okay, that makes sense. And then the labels here are actually not going to be converted to N64 because instead of doing cross entropy loss, we're going to do binary cross entropy loss, which basically says BC loss, which basically says like predict 1 if good, 0 if bad. Our model now is not going to have 2 outputs that are 2 options. It's just going to have one output that says good or bad. And I think that's almost there. So now when we train, we get our data, and we featureize data. We need this to be, so this is our data right now is of the shape batch size, like number of images, or 3, CHW should be. And when we featureize, we kind of want to act like we're not in this case where we have like 3 images per batch. So we're actually going to undo that thing that we just did. So we're going to say features is equal to data.reshape. Can we flatten dimensions 0 and 1 together? Yeah. And featureize also has like a second input, which is the model. Like this. Okay. Features now has to be reshaped back into B3CHW. Okay. That seems... Oh, no, it doesn't. Does it? I actually don't know. Let me think. So, no. We have batch size, 3 for number of images, CHW. The fully connected layer at the end expects BCHW. So we actually have to fuck this guy up a little bit. Yeah. So our model, when we make him, we had him say, I want you to take in features somewhere. In features. And we should multiply this by 3 because we have 3 sets of features that we're comparing together. Yes, it's all coming together now. And so, also, we don't know what the shape of this features is. Features is going to be something wacky. He's going to be something that's like big number, question mark. Let's print out features.shape here. Howdy, how's it going? It's going pretty good. Going pretty good. We've got a lot done to say today. So he's 15 by 512. Right, so 512 features per image. And so we want to go from 15 by 512. We want to go from that to 5 by 512 times 3. Yes. So we can say A, B is equal features, shape. Then we can say features equals features, reshape. A over 3B times 3. Yes. Then we feed that into the last layer of the network. Classifier model FC features. Output is this. Woo! That might just work. Maybe. Maybe not, but maybe. Okay, so that features shape doesn't like that because it got floats because these fucking... Dude, in Python, when you divide two ints together, they turn into a float. What fucking language does that, man? I mean, it makes sense, right? Because you don't want to, like... If you don't want people to worry about, like, weird integer math, like, I guess that it makes sense, but just... Oh, fuck! Okay. So what's happening now? Our criterion output labels... expected 5-1, but it's 5, so our labels need to be reshaped a little bit. So our labels just like an unsqueeze 1, I think. Put them at the right. With double divide, you keep int. That's crazy. I didn't know that, but that's wild. All right, I mean, sure, fuck it, I guess. Found D-type bool, but expected float. Let me double check what the expected like BCE loss input is. I kind of just assumed I knew it. So his labels, I thought that it was just 1 or 0, true or false. Input were any number of dimensions, output same shape as the input. So loss is M input target. Oh. What the hell? I thought it was just... I thought that this was true or false. Which one of these is like gives me just yes or no answer? Where is my criterion? Hello? BCE loss. Cross entropy loss, L1 loss. I could have sworn it was this one. I guess I could just set this as 1 or 0, I guess. That seems reasonable. We'll try it. Because I'm pretty sure I'm right, but... What do I know? Okay, let's try that. Okay, so we're getting device-side assertion. So let's train once on the CPU because the CPU logs seem to be a little more reasonable. All elements of input should be between 0 and 1. Aha! So who is failing that? Probably the output. So maybe we want this other one with logits loss because that lets me not think about that. Maybe. Maybe. Okay, here we go. So we have something. Certainly this part where I try to validate our inputs now is just going to be fucking wrong. So when we do our testing here is probably going to be similar to what we do here. Features, data flatten, AB, features reshape, output like this. Yeah. So we'll just whoop, shove that in here and then see if the same thing. Let's see if it works. Oh, I guess our labels, our test here is not that the labels equals output labels. So our labels is true or false, and our output is 1 or 0. So our outputs are like some number, probably between negative big number and positive big number. So I think that we just want output labels is greater than 0 here. If it's greater than 0, then it says that it's object A. If it's less than 0, then it says it's object B. And let's just print output labels here just to make sure that we fucking understand. Oh no, we're already doing... This is not max anymore. This is just like this, output. Yeah. Okay, so we should see... That should work. Let's make this... Let's... Yeah, sure. We'll see. There's a good chance that that's not quite right, but it will crash pretty quickly if it's not. We love it when our programs crash. Okay, so our output here... Oh, wow, that's actually working. So we have mostly negative numbers, so I think that I was right that it should be between negative infinity or negative big number and positive big number. And now let's train on CUDA and see if that gains us anything. It could just be that our time is like dominated by image loading though, in which case training on CUDA won't really help us at all, but whatever. Okay. So here, mostly positive. We got 27 correct out of something. I actually don't know. I thought that this was supposed to be a number between 0 and 1, but I guess not. Let's let it get to iteration 50, and let's just see if it starts to do better. I'm hoping that we see numbers here between -1, or we see some numbers that go negative, because if I understand correctly, things that are below 0 are the ones that are image B, and the ones that are above 0 are the ones that are image A. And let's just see if it gets somewhere sane. 34, 35. Ooh. I've been typing too much. Sometimes my wrist starts to hurt a little bit, and I gotta be careful about that. But just means that I have to type a little slower and a little less aggressively. Okay, so let's see what it says here. I'm pretty sure that number has gone down. Maybe not. It started at 6.9, went to 5.3, so maybe it hasn't gone down at all, actually. Maybe I'm just trying to... What's that thing called? Confirmation bias? Where you just, like, see the results that you want to see? Okay, so now we have a couple positive, mostly negative. Oh, no, okay. This number did go up, but I don't know if that's reasonable or not. Like, I don't know what this number is supposed to be. So let's look at this. I shouldn't have canceled. I should have let it run in the background. So we're saying output greater than 0. So something about this seems wrong to me. Output greater than 0. The sum of this, dividing this guy by 50 should never be greater than 1. So there's a bug in there somewhere. So let's print output shape as well as labels shape. Okay. Everything else in here seems reasonable to me. And can we drop this down to like 5? Okay. Just because I want to see, you know? I just want it to... Okay, so here we have 5, 1, and 5. So maybe we need like an output is equal to output.flatten. And then let's print labels is equal to output is greater than 0. Let's see what that provides us. I think there's probably some like accidental broadcasting going on there. Okay, there we go. There we go. And let's bring this back up to 50. Little mistakey, no biggie. No big dealio. So let's see on the first step, what does he say? What does he say? How many does he get right? 42% initially. That makes more sense. Okay. And I guess we just give him a sec and see how he does. What do we do in the meantime? Take a sip of coffee. And hope that this eventually, we could just count. Maybe we just me listing numbers like, you know, like the vampire from Sesame Street? Counting Vampire Sesame Street. Or is it Sesame Park? Which one's Canadian? One of these is Canadian, one of them is American. But he just lists numbers sometimes because, like, for like 4-year-old children, maybe 4's too old. I kind of feel like watching this number, I'm just like that guy. Yeah, yeah. Does he laugh after each one? If I play this, am I gonna get in trouble from Sesame Street?
Because I love to count. 1, 2.
Yeah, this is what I'm thinking.
3.
Okay, that's enough of that. We stalled enough. We went from 42% to 50%, but we actually have absolutely no idea if that's like just luck or not, right? Who fucking knows? The loss number doesn't seem to be like consistently trending in any direction. So we also just don't really know if it's like learning anything. But I do think that like what we produced was pretty reasonable, right? We took 3 images, one of which is ASCII, 2 of which are not, featureized them all, asked the final layer to take all of that input together and to tell us which one it is. And as I will probably have to go back and double check the like labeling there. There's like a chance that there's like a mistake in there. But I'm pretty sure that that's what I wanted to achieve. And so I guess at some point I'm going to have to say, if training this thing just takes a long time, which it might, and like I might have to try tuning some parameters and stuff, it might make more sense for me to kind of cover the rest of this offline, which kind of sucks for like the YouTube video, right? It would be nice if we could say at the end of this, hey, we got something and look, it works now. Because it's hard to say whether or not what I did was correct unless we see some form of results. It does look like this guy's just getting 50% on the nose, which means that he might actually see no signal that's relevant to him. And he might just be flipping a coin, which would kind of suck. Could be learning rate is too high, or that he's just, yeah, flipping coin. Who knows? I'm going to give it one more chance, maybe step 150. And if we see some improvement, then we can feel good about ourselves. And otherwise, we'll have to probably call it a day. So those of you who are around and watching, appreciate it. Thanks for watching. If you liked what you saw, I stream most days around 1 or 2 o'clock Pacific time for around 1 or 2 hours. If you miss stream or you don't want to watch live for whatever reason, you can catch me on YouTube. There's a link in the Twitch description. And if you're watching on YouTube and you want to come say hi, tell me why what I'm doing is wrong, you know, there's a Twitch link in the YouTube description. Code for this stuff generally ends up on GitHub. GitHub is like the same as my Twitch and YouTube username, and there's also a link for that. And if you want to talk about shit while I'm off stream, there's a Discord link in the Twitch description as well. Otherwise, looks like this isn't improving, and I've got some debugging to do, so I'll take a look at this off stream and come back tomorrow, and hopefully we get a little farther on this project. Thanks for watching. Catch you on the next one. Bye!